I'm going to talk about solidification in broadly in the context of sea ice, but I want to be very general. And from my perspective, sea ice is an example of a solid formed from a mixture of two components. In the case of sea ice, we're talking about water and salt. And so really my lectures are going to be quite general about solidification of two-component mixtures. But all my examples will be drawn from sea ice, so in particular, I will consider the solid phase to be pure ice, and that'll just simplify the notation, simplify the language, so whenever I talk about ice or solid, I will use those two things interchangeably. Okay, so we're going to start out with an experiment with good science. I want to hand these out. Please don't fiddle with these until I tell you to. Okay, so I'll put one there. There are not too many. Put one here and maybe go behind. Yeah, and then one at the back there. But the people, actually, no, a row in front, and then you can turn round going back. And I give one here and face the back row. Okay, so I'm handing out some plastic bags of liquid. One of the bags is a bit degraded and has a few solid crystals in it. Please ignore those, they're not there. This one, I'll give it to the lecturer so you can pretend. So when I say go, you'll see there's a little metal disc inside. Just grab the disc and bend it slightly when I say go, not before. And I want you and your colleagues around you to make observations, qualitative observations and quantitative observations. Qualitatively, use all your senses, whatever you see. Quantitatively, I want you to answer a very simple question. You will see something happen. I want to know the rate at which it happens. In particular, does the rate decrease with time? Is the rate constant in time? Or does the rate increase with time? Okay, so just three choices: decrease in time, constant, or increase. So try and make that observation and get a rough sense of the order of magnitude, okay, of how fast things are going. Okay, are we ready now? Okay, so try and see what's going on if you can. Ready, steady, go. So I'm hearing some qualitative observations. They show it's hot. Yeah, and do pass it around with what you're finished. You can also, manhandle it a little bit. We started out with a bag full of liquid. So perhaps the first observation is, what do we now have a bag full of? Really? Solid? Soft. Okay, so it's more solid than it was, but it's soft. Do pass it around, do play with it. So actually we have a mixture there of some solid crystals and liquid that's left behind. Someone already preempted me. The scientific name for what's in the bag is mush, or a mushy layer I will talk about. And that's what sea ice is. This stuff in the foreground looks like solid ice, but it's not. It's a mixture of ice crystals and liquid. And we're going to try and understand that composite material. We've already observed that there was heat involved in this change. And we saw that transformation from liquid to mush happen at some rate. So hands up if your observation was that that rate slowed down with time. Constant in time. And sped up with time. Okay, I think it's unanimous for constant in time. So we'll see if we can make that prediction as we go through. Anything else I've missed that anyone observed that I haven't mentioned? I don't think so. I think I've covered all bases. Okay, first observation, it's hot. So Yeah, so there was a nice front. It was sort of an envelope, because actually if one took a microscope, one would see quite a complicated front. That's very important. And we'll talk about this much more on Wednesday, we are not going to be looking at the individual boundary between solid and liquid, which is actually on very small scales, but we are going to look at that smooth front. We're going to treat this two-phase material as a continuum material with, as you say, a nice smooth front, and that's going to be important. Good. The first observation was that there was some heat, so we ought to think about heat. And I'll start here. You'll notice my very first slide has lots of mathematical symbols and equations on it, and that will be characteristic of a lot of my slides. There will be a lot of equations, and I want to just say something about how I'd like you to approach that. What I will try to do, and what I'd like you to try to do, is to take from these equations what the physics is that's being described. I will try and describe physics through mathematical expressions. Some of these expressions will be familiar to you, to some of you at least. You will have seen similar sorts of equations. I won't, for the most part, discuss how to solve those equations. Okay? So we'll use this as a means of describing the important physics, what's involved, what material properties are involved. I will give some indications about certain sorts of solutions, but if you want to know more details, you might be able to fill in the gaps yourself. If you've got some mathematics, do come and ask me questions at any time. I'll be very happy. So, heat. The heat that we're going to talk about, sometimes called enthalpy, and that's because all the processes I will talk about will be done at constant pressure. And at constant pressure, it's most convenient to work with enthalpy. It's the heat per unit mass, so specific relates per unit mass. Specific enthalpy, heat per unit mass at constant pressure, and that will be true throughout the lectures. Okay. We start with a conservation law, and all conservation laws have the same form. They have the form of a time rate of change of the density of stuff, the density of something. In this case, the density of heat per unit volume. And because we're starting with a heat per unit mass, I need to multiply by the density, the mass density, mass per unit volume, to give me a heat per unit volume. So all conservation laws, rate of change in time of material per unit volume, heat per unit volume, plus the divergence of a flux is equal to 0. So this is a canonical conservation law. Here for enthalpy, we have to know what the flux is, and there are two types of flux of material. One is an advective flux, which basically says if I have a property of a material, then I can carry that property if I move the material. So in particular, if I have a property of a liquid or a fluid, and that fluid flows with some velocity u, then I have a flux of heat, in this case by multiplying the fluid velocity by the amount of heat per unit volume. So that gives me a so-called advective flux, and then there can be a gradient flux. And in the case of heat, we know that heat travels from regions that are hot to regions that are cold. Heat travels down a temperature gradient. Hence the minus sign, minus the gradient of the temperature, and the constant of proportionality, little k, is the thermal conductivity. So let's take this expression and put it into our conservation law. The first thing we do is apply the product rule to this time derivative. So I've got rho dh dt plus h d rho dt. That's that first term. I've then got the divergence of the advective flux, and I'll use the product rule again. So h times the divergence of rho u plus rho u dotted with the gradient of h. It's just the product rule. And then I've got the divergence of my diffusive flux, which I've put on the other side. I've colored these two terms a little lighter because you'll see sitting in there, if you factor out the h, d rho by dt plus the divergence of rho u. So we've got another conservation law going on in here. rate of change of density plus the divergence of mass flux, advective mass flux, and by mass conservation, these two terms add up to 0. So mass conservation gets rid of those two terms, and I'm left with rho dh dt plus rho u dot grad h, which is rho, the density, times the material derivative of h, is the divergence of the diffusive heat flux. And now note that there's a quantity called specific heat capacity, which is the rate of change of enthalpy, heat, rate of change of heat with temperature at constant pressure. And I can use that with the chain rule to change material derivative of h to the material derivative of temperature multiplied by the density and the specific heat capacity. And I wanted to go through this in particular to give the form of this equation. And I want you to note in particular where these material parameters appear. Because on Wednesday in particular, we're going to look at situations in which the conductivity or the specific heat capacity are not constants. We need to know where they sit. The conductivity properly sits inside this divergence, and that's a mistake that some people make. They sort of leave it outside and write this as k del squared, which is okay if k is constant, but not if k is variable. And then some people also put this rho Cp in analogy with this. They want to put it inside the time derivative, and it doesn't belong there. This rho Cp always belongs outside the time derivative, and this derivation shows why. Okay, so the other important equation is what happens at interfaces, and we've seen a phase boundary moving. So if I now just think about solid and liquid, so not as complicated as in the bag. So a liquid freezing to form a solid, and at some rate v. If I take a frame of reference that's fixed in the solid, then there's no motion of the solid, but I might have fluid motions in the liquid region, UL. This is a slightly difficult picture to analyze because it's not a steady picture. If I looked some time later, this interface will have moved. It's much easier to work in a frame of reference where the geometry, the picture, is fixed, and we can do that by moving to a frame of reference where we move ourselves, we move our camera with that phase boundary. And as far as I'm then concerned as the observer, the solid is receding behind me at the solidification rate v, and the apparent fluid velocity has also been modified by that solidification rate v. Now, in any frame of reference, but in particular in this frame of reference, because the picture is steady in this frame of reference, the normal heat flux must be equal on both sides of the interface. The heat coming into this interface is equal to the heat going out of the interface. That's that statement here. We have expressions for the heat flux from the previous slide. So we have an advective heat flux and a diffusive heat flux in the solid and in the liquid. I'll rearrange terms a little bit, and I've got my HS minus V, and then I've added in a term which doesn't appear on the previous line, but immediately taken it away. This rho L HL, rho S HL times V, and then this term comes from here, and here are my diffusive terms. The point being that now again in this lighter shade of blue, we have an expression of mass conservation at the interface. So by conservation of mass, this term is all 0, and what I'm left with is that the difference in heat content between liquid and solid. So if you think of changing ice into water, I have to add heat to melt the ice. So water has a higher heat content than ice. HL is larger than heat content for liquid, larger than that of the solid. The difference is called the latent heat. And we've got here sitting HL minus HS, so that's L. And I've got the density of the solid times the latent heat times the rate of solidification is equal to the difference in the diffusive heat flux either side of the interface. And notice there's no mention of any velocity, any fluid velocity or anything in here. It's purely the diffusive heat flux difference. This is perhaps the most important equation of the course. It's called Stefan's equation, or the Stefan equation, and it tells us how phase boundaries move given the mismatch in heat flux either side. Okay, so let's get into sea ice, and we'll go back into the 19th century. First polar year, 1882 to 1883, organized by someone called Carl Feiprecht, who organized the thing, I think, through the auspices of the Austrian Academy of Sciences. And they got stuck in the ice for 2 years, actually. So the polar year turned into polar 2 years. But they had spent that time measuring the thickness of the ice as it varied with time, deposited that data with the Austrian Academy, where it was picked up by Stefan. And this is the same Stefan as in the Stefan Boltzmann constant of radiation. They did survive. And they got back, and most importantly, they were able to present their data. So this is what we care about. Okay. So we have the data. Can we make a mathematical prediction of it? Well, here roughly is the problem. We have the warm ocean. The ocean is roughly at its freezing temperature, which is about -2 Celsius. But that is warm compared with the atmosphere. Let's take a representative temperature in the Arctic of about -20 Celsius. So we have a temperature difference between the ocean and the atmosphere. It's a conduction of heat through the ice, and we'll just treat it as a solid block of ice and imagine that the ocean is all at its freezing temperature, Tm. And we want to solve this equation subject to boundary conditions. So something I will do from time to time is to at least count boundary conditions, see if we've got enough boundary conditions for the equation that we're trying to solve. And here we've got this diffusion equation, which has 2 space derivatives. And so I need 2 boundary conditions. Well, they're here illustrated. I've got the temperature is equal to the freezing temperature at the interface between ice and water. I have the temperature is equal to the surface temperature, which I measure or impose in a laboratory experiment at that. So that would be fine if I knew where the boundaries were. But here, one of the boundaries is an unknown. I need to discover where that is. And so I need an additional condition. And that additional condition comes from this very important Stefan condition, rho L times the rate of change of phase, in this case dAdt, is equal to the mismatch in the conductive heat transfer. And this is one-sided because there's nothing happening on the liquid side. So it's just the thermal conductivity times the temperature gradient in the ice. Okay. So there's our mathematical problem. And this is often known as Stefan's problem. So I say Carl Feiprecht presented his data. Stefan's problem, as data was presented in the 1880s. Turns out Stefan's problem was solved in the 1860s by Neumann in a series of lectures. And his solution goes something like this. We have a diffusion equation. Here are the 2 boundary conditions and the extra Stefan condition we need to determine the position of the boundary. We're going to start just thinking about scaling. There's an obvious temperature scale in this problem, which is the difference in temperature between the interface and the boundary. There isn't an obvious length scale or time scale in the problem that's specified, but there may be intrinsic, internal length or time scales that we can discover by considering the physical balances or the mathematical balances of what's describing that physics. So if we look at the diffusion equation, we can see that the order of magnitude of this term is a temperature difference over a time scale, delta T over tau. And that should balance the size of this term, which is a thermal diffusivity. And I see that I haven't put that on a slide, and I should have. This is thermal diffusivity, is the thermal conductivity over the density times the specific heat capacity. Okay? And that's come from the previous. We used to have rho Cp dt dt as k d2 t dz squared. I've divided by rho Cp and turned that into a kappa. So on this side we have the diffusivity times the temperature scale divided by the length scale squared. And if we sort that out, the delta T's cancel, and we see that H scales like the square root of the thermal diffusivity times a time scale. In principle, there's another equation. This could set a different length and a different relationship between length and time. But if we look at it, we've got rho L characteristically H over tau. Scale for that term, we've got the thermal conductivity K, and then a temperature scale over a thickness scale H. And if we rearrange that, we have that H scales like kappa tau over some non-dimensional parameter S, which comes on a later slide. So let me write down what it is here. S is L over Cp delta T. Very important parameter in this subject. But both of these tell us that H is proportional to, this is just a constant proportionality, proportional to the square root of diffusivity times time. So although I thought I had two relationships to determine two scales, actually they both give me the same information. There's a redundancy here. And that is an indication that there's a special sort of solution known as a similarity solution. The only time scale in this problem is the time that's elapsed since the initiation of the problem, since the start of the problem. So we have to choose the time scale to be the elapsed time t. And if we scale our variables by factoring out our temperature scale and having a dimensionless temperature theta, and then t is a function of z and t, but we want to use dimensionless variables. So we scale z with h, we scale t with tau, but we said that the only time scale tau is t, and so t over tau is just 1, and z over h is z over the square root of kappa t. So whereas we thought we had a function of two variables, it turns out that we have a function of this new variable, z over root kappa t, and a constant 1. So actually we have a function of just one variable, which I've called eta. Okay, so this is known as a similarity solution. It's a very nice approach to solving various problems. If you simply take this and substitute into our equations, you get this set of ODEs. And I'm not going to spend time on them. They're there for reference for you if you want to work through the details later. This is an ODE which is solvable by elementary means, and you can go through and make substitutions. Here is the all-important Stefan number that I mentioned just now. The ratio of the latent heat to what's also called the sensible heat. Sensible so it's an archaic use of an English word. So it's sensible not as in reasonable or intelligent, but sensible in that you can sense it. You can touch it. So this is the heat that you can sense because there's a change in temperature associated with it. And this is latent heat, hidden heat, because it's a change of heat content without change of temperature. Here's the solution, solved in terms of error functions. Again, I don't want to go through the details. The important property is that the thickness of the ice, which we're trying to predict and compare with Pfeiffert's data, goes like the square root of kappa t. Okay. Good, and here's just some information about the error function. So that's our first mathematical prediction. We have solidification. Solidification goes like the square root of kappa t, which is a rate that decreases with time. Okay, so this is obviously different from what was happening in our plastic bags, where I think we all agreed that we had a rate that was going at a constant rate. So there's something different. And of course, the problem I've given you is more like growing ice cubes in your freezer, because we've imposed a cold temperature at a boundary, and we have ice growing away from that cold boundary. In the case of the plastic bags, we initiated some crystallization. We'll talk about that in a little later. Initiated some crystallization, and then that grew. So, okay, we didn't initiate it by introducing a cold boundary. It initiated almost, well, we'll talk about it later. Okay, I want to introduce you to a very important approximation that we will make a lot of use of, just to keep things straightforward. Let's go back to our equations, and I'll scale temperature difference with this obvious temperature scale, so nothing's changed there. I'll scale times with some time scale tau, and I'll scale lengths not with root kappa tau, but with root kappa tau over s. Okay? And what I've done there is, rather than choose a scaling in which the terms in the diffusion equation balance, I've chosen a scaling in which the terms in Stefan's equation balance. Okay? So with this scaling, my dimensionless equations, scaled equations, look like this, with two terms in Stefan's condition. But in the diffusion equation, I have the time derivative multiplied by a 1 over Stefan number. And so if the Stefan number is very large, and we'll mention some numbers in just a moment, then this term is very small, and instead of having to solve a diffusion equation, I can solve Laplace's equation, which in one dimension is just the second derivative of t is 0. We can almost solve that in our heads. If the second derivative is 0, then the first derivative is constant. If the first derivative is constant, then we just have a linear temperature profile, constant slope through our ice, rather than this curved error function profile that we calculated just now. And we can do that very easily analytically. Now in our Stefan condition, we have the latent heat release is balanced by the temperature gradient, and the temperature gradient from this linear profile is just the temperature difference divided by the thickness. Okay? And then we can almost solve this equation in our heads, multiply up by a, and we've got a times dA dt. The integral of that is a squared, modulo factor of 2. And on the right-hand side, I have a constant which integrates to t. So take square roots of both sides, and I find this nice result that a goes like the square root of kappa t over s. And actually, this agrees very, very nicely with that Neumann solution with error functions when s is large. So this is a very convenient approximation in these circumstances. So is this a reasonable approximation to make in real practical situations? Well, L over Cp for water is about 80 Kelvin, okay, 80 degrees Celsius. So if delta T is small compared with 80 Celsius, then this Stefan number is large. So even in my example that I had up earlier, where I had a surface temperature of -20 and seawater at -2, temperature difference roughly 20 degrees, this Stefan number is 4. And actually 4 is a pretty big number, it turns out. No, seriously. It's a pretty big number in terms of making really quite accurate predictions of what's going on. Okay, and I'll mention this more on Wednesday. This seems very crude and approximate. This actually is the basis of what's known as the zero-layer Sempner model for sea ice growth. It is in this is the level of modeling that is in most general climate models today. There are modifications I'll tell you about on Wednesday, but this is our starting point for modeling sea ice. Okay. Yeah, good time. So, I want to extend our sort of toolkit and our language around this subject, and we're going to introduce some other geometries and some other considerations. So, let's go back to the bag. As I said, we didn't cause solidification in that case by introducing a cold boundary. Somehow we triggered solidification, we'll discuss that later, by flexing the metal disk, and then crystallization happened at some rate. Why has it done that to me? Let me just escape from that for a minute. Let's restart it and see if that helps. Okay. The reason that could happen is because the liquid in the bag that I gave you was below its freezing temperature. Okay? It was in what's called a metastable state. It was not in a complete equilibrium state, and we were able to disturb that equilibrium and allow the system to return to its equilibrium state, so that the hot temperature that you felt at the end is actually the freezing temperature of that liquid. So these bags can be reused, which reminds me to say, please may I have them back at the end of the lecture. They can be reused. You just raise the temperature above the freezing temperature, all the crystals will redissolve, and then if you cool it slowly, you can arrange to cool it to below its freezing temperature without any crystallization. And then we come in, we make a big perturbation to it, and we get crystallization. In other words, we have crystals growing into what's called a supercooled melt. So that's the next example I want to think about, is I'm going to take a spherical object, solid, growing into a supercooled melt, a melt whose temperature is less than its melting temperature, freezing temperature. Heat is going to get generated as this solid grows. It's going to get hotter. That's what we observed in the bag. And that heat is going to be dissipated through into the liquid. And we're going to go straight to using the quasi-steady approximation, assuming that the Stefan number is sufficiently large. So instead of solving a diffusion equation, we're simply going to solve Laplace's equation. And in spherical geometry, the fundamental solution of Laplace's equation is 1 over r. Typical potential for Laplace equation, just a 1 over r potential. And that's what the temperature field looks like. And then if we put that into the Stefan equation, we get, again, the rate of release of latent heat minus the thermal conductivity times the temperature gradient. Let's do this. d by dr of this is minus 1 over r squared. So I have a minus a over a squared, which gives me minus, cancelling that, minus 1 over a. So same sort of equation we had before, and we can solve this, give us the same form of solution. So we still haven't got to what's happening in the bag. Okay, we still have a solution. So this is now solid growing into a supercooled melt, and it grows at a rate that is decreasing in time. Size of this sphere looks like the square root of time. Well, these weren't spheres. Somehow there was a planar front. Maybe it's different with a planar front. Let's look at the planar front, and yeah, try and finish. Here we have a problem in using this quasi-steady approximation, and that's because we want to solve the diffusion equation in this external region, this mathematically infinite, semi-infinite region outside of the crystal, and there's no steady state in the infinite domain. So I'm going to take a slightly different approach and use conservation of heat directly in an integral form. So we have to conserve the overall heat content of this system, and the heat content is made up of the heat content of the solid, and with respect to the temperature at infinity, that's the specific heat capacity times the density, so heat per unit volume, times the temperature difference. And here I am assuming that material properties like specific heat capacity are constant. And then because this is solid, and I'm taking as my reference the heat content of the liquid at infinity, I need to subtract the latent heat, okay, to turn it into solid. So this is the heat content of the solid region up to A of t. And then I need the integral, the heat underneath here. The heat is the integral of the sensible heat, rho Cp times the temperature difference over there. And this may seem very crude, but actually this gives extremely accurate answers, even better than the ones we saw before, is I'm simply going to say this has some characteristic size delta, and I'm going to approximate this integral by this enthalpy difference times delta. So approximate that integral of the temperature is just the temperature difference times delta. And if I put that into here, I find that delta is approximately the Stefan number minus 1, okay, times A. And then if I put that in the Stefan condition, divide by this delta, I've got this extra factor of S minus 1. And we find that A looks like the square root of 2 kappa T, we've seen that before, divided by S, which we've also seen before, but now divided by S minus 1. And now we might start to worry, because we're dividing by something that could possibly go to 0. So this expression is fine, actually gives you very accurate answers, provided the Stefan number is larger than 1. Obviously tends to infinity as the Stefan number approaches 1, and doesn't exist, because this would be negative underneath the square root sign, if the Stefan number is less than 1. So I'm going to take a short break. I'm going to leave you with that riddle, and we can just stretch our legs for a little bit. We'll come back. It's 9:32. Let's try and start at 9:40, and we'll pick up and try and resolve this conundrum. Okay, so we finished the first half of this morning's lecture with the rather uncomfortable conclusion that our mathematics had made a prediction that the solidification rate was going to tend to infinity if the Stefan number approached 1, or that my solution doesn't exist if the Stefan number is less than 1. Well, usually when mathematics of physical systems throws up infinity in your face, it's because we've forgotten some important piece of physics. We've made a physical assumption that isn't right, and we need to correct it. And that's actually why I mostly enjoy applied mathematics. It's this sort of back and forth between experiment and mathematics, where you start with a physical system, you try and describe it mathematically, use the mathematics to make a prediction, and then find that it sort of blows up at you, and so you have to go back and re-examine your physical assumptions. So what's gone wrong here? What in our system, everything I've said sort of feels physically reasonable, but something is obviously wrong. And the thing that's wrong is that it's hinted at by the fact that this is going very fast. If it's growing very fast, if the Stefan number approaches 1, then this is not a near equilibrium situation. And I just rather quickly said, well, let's assume that the interface between solid and liquid is at the freezing temperature.
As you mentioned, S is usually very big.
Ah. Yeah, and in the bag it's very small. So this is the point, that there are situations, and what happened in the bag is a case where the Stefan number, or the effective Stefan number, and I'll see what I mean by that later, is less than 1. Okay. So in those situations, we are far from equilibrium. The freezing temperature is an equilibrium temperature. It's a temperature at which solid and liquid can coexist in equilibrium. It's a very dynamic equilibrium. Actually, even if I have solid ice and water at 0 degrees Celsius, at the molecular level, there are molecules of water that are turning and forming into ice, and there are molecules of ice that are turning into water. Okay? And that's happening at about 1,000 molecular layers per second, if you average it out. So it's sort of one molecular layer every millisecond. But you know, that's the sort of rate we're talking about. So it's a dynamic equilibrium. And if our phase change is happening faster than that, we're really not in equilibrium. We really shouldn't be assuming that this interface is at the equilibrium freezing temperature. In order to advance, we need the rate of attachment, rate of change of mobile liquid molecules into immobile solid molecules, to be more rapid than the opposite, than the ice turning into liquid. And in consequence, the interfacial temperature actually needs to be less than the equilibrium freezing temperature. Okay. And there is some kinetic law. There are different types of kinetic law depending on exactly the nature of the crystalline interface. The simplest kinetic law is simply to relate the growth rate V linearly to the temperature difference between the equilibrium freezing temperature and the actual interfacial freezing temperature, which must be less than Ti. So in some non-dimensional sense that we could define, G is typically a large parameter, and sort of when we're growing ice in our, or growing sea ice, growing ice in our freezers. So if G is large in some appropriate non-dimensional sense, then Ti is very close to Tm. G is large, this difference is small, and the approximation that we used before is a good approximation, but it is only an approximation. Okay. So let's see if this helps us out of our difficulty. If we're moving very rapidly, and our previous mathematics tells us that actually we will be going to move very rapidly. Oh, and we ought to think about that. Let's just go back to our experiment. We did make some, I'd like to make a quantitative measure. You have to think back to the bag. I love estimating to orders of magnitude. So you have to tell me, order of magnitude, was that phase change happening at a millimeter per second, a centimeter per second, 10 centimeters per second, a meter per second? Okay. Millimeters per second, I've heard a centimeter per second. Yeah, maybe a centimeter per second. So, or another way of saying it, this bag was, 10 centimeters, okay? And it took about 10 seconds. Let's think of the diffusion time. So thermal diffusivity is, in centimeters, is about 10 to the minus 3. In 10 seconds, you've got 10 to the minus 3 times 10 is 10 to the minus 2. The square root of, 10 to the minus, where have I got to? 10 to the minus 2. The square root of 10 to the minus 2 is 10 to the minus 1. So the square root of kappa T is a tenth. Should have got about a millimeter in our 10 seconds. And it didn't go a millimeter, it went 100 times that. So this growth was very rapid compared to the diffusive time scale. Okay. So Now, given it's very rapid, we've left the original position a long way behind, and I'm going to forget about that. I'm going to fix myself at the interface and just move at that speed. And in that frame of reference, I've got an apparent advection with the frame rate minus v dt dz is my diffusion. I can solve this very easily with exponentials. That's given here, and back into my Stefan condition. I get here, notice now my Stefan condition no longer determines V. Okay? Stefan condition is an equilibrium condition. It's not actually a condition, it's not actually a kinetic condition for V. We can use it in that way, it turns out, in many circumstances, but here it doesn't. What it does is to determine this interfacial temperature, Ti. Okay? And we find it's related to the Stefan number and this temperature difference. We can put that interfacial temperature into the kinetic growth law and find out that V, in this case, is equal to our kinetic parameter G times our temperature difference Tm minus T infinity, that's a material property, times 1 minus S. And this works out for S less than 1. Okay? And notice that V is constant, independent of time. So actually here we have recovered what we saw in the bag. We've got a change of phase at constant rate into our supercooled melt in a situation where the Stefan number, or effective Stefan number, is small. Let me say something about that very quickly, because it will be elaborated more on Wednesday. The effective Stefan number is the actual Stefan number times the solid volume fraction at the interface. And it's because actually what was happening in there was a lot of little crystals growing up like this, albeit with a smooth envelope. The solid fraction is not very high, and so there's not much latent heat release at that interface. So that effective Stefan number is low. Okay, so that was happening. Okay, yeah. This is empirical, okay? And this has different, this is appropriate for a solid which is molecularly rough, okay? Which has what's called a low entropy of fusion. So if you think of, your childhood experiments growing copper sulfate crystals or whatever, you can get nice faceted crystals, Those are molecularly smooth, okay? And they have a very different kinetic growth law, okay? You can also, and they grow essentially by, attachment of one molecule, which takes a lot of energy. Once you've got one molecule onto that facet, you can add lots of molecules at low energy cost along, and so you tend to grow things in layers and keep that facet growing. And that gives you a more like an exponential kinetic law. There's another form of growth which is called screw dislocations, where you grow material as sort of spirals on that. That tends to give you a quadratic law. I've just used this mostly for mathematical convenience. Turns out to be a good model for molecularly rough surfaces. Okay, but it is an empirical law. Okay. Okay, so this is one sort of undercooling that we have to be conscious of, although we're not going to spend too much time worrying about it. It was nice to get back to the bag. And the form of undercooling that we are going to worry a lot about relates to curvature. So far we've been talking about, well, mostly one-dimensional flat interfaces. We did talk about a sphere, but had in mind, at least I had in mind, fairly large spheres. I'll come back to that in a minute. We have to worry about the effect of curvature. So an equation I won't spend a lot of time on. Alan will spend a bit of time on this as well. Is the Clausius-Clapeyron equation. So this is an equation that tells you actually the equilibrium at a solid liquid phase boundary, taking into account pressure differences. So I started beginning of this morning saying I wasn't going to worry about pressure differences, and we'll work with enthalpy. Actually, we do have to worry about pressure differences a little bit, particularly if there's a pressure difference between the solid and the liquid. So let's just read this equation. It's the mass density, the solid density, the latent heat. We've got the difference between the equilibrium freezing temperature and the actual interface temperature. Okay, and that's a difference. This is the absolute temperature, Tm, measured in Kelvin. On this side, I have the pressure in the solid phase, the pressure in the liquid phase, okay, actual pressures. And in this term, I've got the pressure in the liquid phase relative to the pressure at which this equilibrium freezing temperature was measured. So when I say the freezing temperature of water is 0 degrees Celsius, I ought to be saying freezing temperature of water at standard atmospheric pressure is 0 degrees Celsius. So if the actual pressure is different from my standard atmospheric pressure, then it changes from Tm, and it changes according to this density difference. So let me just do two very quick checks on you. If we think about the Earth's core is mostly iron. Iron has a larger solid density than a liquid density. So this term is negative. The pressure at the center of the Earth is much higher than atmospheric pressure. And so this will give you, this tells you that the, gives you depression. It raises the freezing temperature. It tells you that the very center of the Earth is solid, even though it is the hottest place of our globe. So the center of the Earth is the same temperature as the surface of the sun, about 6,000 Kelvin, okay? But it's nevertheless solid because the freezing temperature of the iron has been elevated by the very high pressures down there. Conversely, if we think about ice, whose solid density is less than the liquid density, then the freezing temperature is depressed, and you're probably all aware if you push hard enough on ice, then it will melt. Okay. All right. Now let's think about a curved interface. Think of a bubble. If I have a curved interface with surface tension, then the pressure inside the sphere, inside the bubble, is higher than the pressure outside. And the pressure inside minus the pressure outside is the surface tension, gamma, times the curvature. So here's just a nice expression. Curvature is the divergence of the surface normal. And for a sphere, the curvature is 2 divided by the radius of the sphere. So I'll make use of that. And if I put all of this together, we're not worrying about this term, because we're going to worry only about standard atmospheric pressure. We are going to worry about this. There's difference in pressure between solid and liquid at a curved interface, and that will give us a depression of the interface temperature related to the curvature. Yeah. It's the equilibrium temperature. So if I combine it with my previous slide, I'm ignoring kinetic undercooling here. So this is the new equilibrium temperature. Okay. You could make this nonlinear, but with a condensed material like a liquid or a solid, the density is not a strong function. Okay, so let's come back to our sphere and realize that I shouldn't have Tm here at the surface because this is curved and there's no kinetics in this calculation. Okay. So I'm still assuming equilibrium, but my equilibrium interface condition depends on the curvature of this sphere. Okay? So same equation as before, except I replaced Tm with Ti. Okay? And Ti is Tm minus my Gibbs-Thompson undercooling. Okay? Otherwise it looks the same. If I had no surface energy, I would just have what I had before, A dot's proportional to 1 over A, and I'd have got my square root of T growth. This term is negative, and it says if A is small enough, 1 over a squared is going to be bigger than 1 over a, and this negative will come in, and the sphere will melt if the radius is smaller than some critical radius, AC, which is given by this expression. Okay? And if you put in some numbers, it's about 6 nanometers, so not very big. So if I'm really talking about a hailstone or something, then we really can forget about all of this. But it matters because of nucleation. So going back to our bags of liquid, why was it that we were able to cool the liquid down below its freezing temperature without it all turning into solid immediately? And the answer is because in order to create some solid, we first have to nucleate the solid. We have to have a piece of solid that's big enough to overcome surface energy. Okay? And that's a very, very hard thing to do, and we almost never do it. So this is a calculation of what's called homogeneous nucleation, the ice growing spontaneously in the middle of a liquid region. And the energetics of that are very unfavorable. 6 nanometers doesn't sound very big, but of course that's about 1,000 molecules would, by thermal fluctuations, have found themselves together to form a critical nucleus before it can grow. Okay? So in very rarely talking about homogeneous nucleation, we can reduce this barrier by growing onto a substrate. Okay? And that's where that metal comes in to nucleate the growth in the first place. Okay? So I want to keep this in mind, this number, a few nanometers, we'll come back to that. Also, this Gibbs-Thompson parameter can conveniently be written as this, I call it a critical radius. I might also call it a capillary length. Capillary is something to do with surface tension, and this is the capillary length for this system. And we're going to see that coming back in just a moment. Okay. So, this lecture is all about this bag. So far, we've talked about a solid growing at a planar interface, at a spherical interface, but at a sort of macro scale, it's been a smooth interface between solid and liquid. And that's not what happened in the bag. We ended up not with a solid, we ended up with a mushy layer mixture of solid and liquid. So why did that happen? It happened because, as we'll see mathematically, if we are solidifying into a supercooled melt, which is what we were doing, then the interface between a solid and a liquid, if we assume that the interface is planar, and then perturb it a little bit, we find that interface is unstable to perturbations. Okay, it cannot remain planar. So we can't grow a nice ice cube to put in our gin and tonics, okay, if by supercooling the liquid first. We have to do that by cooling from a boundary. Okay. So I'm going to take this through this at a sort of medium pace, at which I hope you can follow the approach, if not every mathematical step. So we're going to start out with the one-dimensional solution that we had growing into a supercooled melt. Now remember, in detail, that required an interface temperature that was kinetically undercooled. I'm going to sweep a lot of details under the carpet. They're sort of technical. Just trust me that everything I tell you is kosher or can be made kosher. In effect, I'm going to be doing this at Stefan number equals 1, okay, which allows that sort of linear growth, constant growth rate with an exponential profile in the liquid. Okay. That'll be hidden from you in what I show you, but for complete honesty, that's really what's going on. Okay. So we're going to start with a planar interface, and I'm going to move myself into a frame of reference that's moving with that unperturbed interface. Okay. And I'm going to call that z equals 0. It is a moving interface. Okay. And then I'm going to add a perturbation. So z is equal to 0 plus eta. So eta is now going to be a small quantity, small perturbation. And I'm going to allow that to vary sinusoidally in the transverse direction, which I've labeled with x, and exponentially in time. So we're doing a Fourier analysis, really. We're thinking about a single wavelength. We could do a general disturbance by adding lots of these different frequencies together, but don't worry about that. We're taking a sinusoidal perturbation, and we're going to ask the question, does this parameter sigma, called a growth rate, is that positive or negative? Because if sigma is positive, then this perturbation will grow exponentially in time. These small corrugations will become big corrugations that form the crystals that went into the bag. Okay. On the other hand, if sigma is negative, then random perturbations will just decay, and we'll be back to our planar interface. So our goal really is to determine this sigma, this growth rate, and to find out the conditions under which sigma can be positive, and I'll get morphological instability growth. So we'll start with a temperature field that decays exponentially into the far field. That's the form that we saw before. And we're going to add to it a small parameter, perturbation, theta, which can depend on z, direction into the liquid, the transverse direction x, and on time. And I'm going to make two approximations, and this is where I've really put a lot of things under the carpet where you can't see them, so as not to clutter the slides. One seems straightforward because we've talked about it already. That's a quasi-stationary perturbation. So I'm going to solve Laplace's equation. Strictly speaking, in this frame of reference, the quasi-stationary perturbation should give me Laplace's equation is equal to the minus v d theta dz. So I still need the frame advection. It turns out I can neglect frame advection if I think about large wave numbers, small wavelengths. Okay, so this approximation we've justified before, and that will be appropriate if the Stefan number is reasonably large, which we can argue about, and then large wave number is the additional one. But it's sort of a detail. But it just keeps the mathematics sort of clean for these slides. And it gives us the right answer. That's the important thing. Okay. So we're simply going to solve Laplace's equation for this temperature perturbation theta. And that's very easy to do. We know that because of linearity, that theta is going to depend on e to the I alpha x. And in order to solve Laplace's equation, that e to the I alpha x must be multiplied by an e to the minus alpha z. So this gives us d2 by dx squared is equal to d2 by dz squared. We might check that. Sorry, d2 by dx squared plus d2 by dz squared is equal to 0. Okay. So decaying exponential, sinusoidal in the transverse direction, and possible growth in time. Okay. So once we've got the temperature field here, we can think about our two interfacial conditions. One is the interfacial temperature, where the equilibrium temperature, the interfacial temperature, is now dependent on the curvature, and the curvature is the second derivative of the interface displacement, hence the 2 alpha squareds. So that's the temperature at eta, at the perturbed position, but I can use a Taylor series to map that back to eta equals 0. Okay, and so I get Tm is the base state, a delta t times minus v over kappa times eta. This is the first term in the Taylor expansion, and then theta evaluated at 0. And with the Stefan condition, I've got the rate of release of latent heat. So rho LV is the basic state. There's an extra d eta by dt. D eta by dt brings down a sigma. Okay. And on this side, I've got the temperature gradient. So again, here's the base state temperature gradient. Here is the Taylor expansion, the first order Taylor expansion of that term, and then the gradient from the perturbed temperature field. The linear terms are here. I'm not going to spend time on it. These are there really for your later reference if you want to work through the details. And if we eliminate theta naught between these two equations, we get this expression for sigma. Okay, so this is the final answer. And we can plot that up, which I've done on the next slide. Yeah, good time. So here's the expression again. I've rearranged it slightly just to group dimensional terms together. This is really the dimensionless growth rate. The -1 here is a bit of an artifact of the fact that we've used a large wave number approximation. So the theory I've just shown you is not appropriate for small wave numbers. It's not and if you do the proper analysis, not assuming that the wave number is large, then this curve actually comes in quadratically to the origin. But that's just a detail for those of you who are interested. So our theory really applies for large alpha. And one thing that we'll really emphasize just now is that the most unstable mode, so the wavelength that's going to grow faster than all other wave numbers, wavelength that's going to grow, actually does have a large wave number. I'm going to formalize that in just a moment. So this is what we get. We can see it. We've got a -1, so we start here. This curve grows linearly with alpha for small alpha, but ultimately decreases like alpha cubed when alpha is large. Okay, so we can at least see that shape. So linear growth and a cubic decay. So we can see that overall shape. And so we can ask the question, what will we see if we add random disturbances? A random disturbance will have all sorts of wavelengths. Some of those wavelengths will decay, and some of those wavelengths will grow. What we will see will be dominated by wavelengths in this region, wave numbers in this region near the maximum. And some very simple calculus will find us the maximum growth rate as we vary the wave number alpha. That's going to happen when d sigma d alpha is 0, usual way of finding a maximum. And if we do that, we find that alpha max, maximum growth rate, looks like the square root of a constant over a diffusion length times this capillary length that we found just now, this critical nucleation radius, which was a few nanometers. The diffusion length is this thermal diffusivity divided by the growth rate. Okay. So if I invert that, this is wave number. Wave number is related to wavelength. By wavelength is 2 pi over wave number. And that gives us a constant times the geometric mean of the diffusion length and the capillary length. Okay. Diffusion lengths, we mentioned just now, for the sorts of experiments we're doing in the bag, diffusion lengths are sort of millimeters to centimeters, that sort of length in these sorts of time scales. The capillary length is nanometers. So we're going to see instabilities not on millimeters or centimeters, not on nanometers, but somehow on the geometrical mean of those two. Okay, in the middle. And in particular, because it is in the geometrical mean of these, they are much smaller wavelengths than the diffusive length scale. And that's the justification, the sort of post hoc justification of doing my analysis at large wave number. Okay, so it really is large compared with the diffusion length. Okay? And of course, it's this instability that gives rise to snowflake patterns, for example, gives rise to the mushy layer that we had in our plastic bags at the beginning of the picture. The diffusion length for a snowflake is really the size of the envelope. Okay, that snowflake will grow basically limited by thermal diffusion of the thermal halo that's around the snowflake. So that's the diffusion length, and millimeters to centimeters, millimeter to few millimeter scale, probably. The capillary length, we're down a few nanometers. Geometric mean of that gets you into the sort of 100 micron range. So these smallest scale of perturbations here, you should be seeing around the 100 microns versus a few millimeters. So very typical. So that's not quite the end of the story for today. I want to, with quite a whistle-stop tour of different physical processes. Those of you particularly who enjoy skiing will know that when you have a fresh snowfall, you have powder snow. Okay? Very fine-grained snow when it first falls, but a few days later, the snow will be coarser, more granular. So there is a change in morphology with time as that snow settles there and stays there and matures. And that's a process known as Ostwald ripening. So this is an example taken from metallurgical literature. This is a lead-tin alloy, and you're looking at the tin phase. So here you have 3 photographs at the same scale, 250 microns, and you see from 5 minutes to 75 minutes to 1,000 minutes that the length scale has increased. These crystals have become bigger. And the other thing that you see, so these have now been rescaled. So this is 100 microns, this is 250 microns, and this is nearly 600 microns. These pictures look rather self-similar. In fact, there's a beautiful theory, I really like it, but I'm not going to present it because it's mathematically a little challenging, that can predict the probability distribution of crystal size in a coarsening medium like this. What I will do is just take you through the scaling analysis that will tell you the rate of coarsening in a system of this sort. But it's just lovely to see that you've got this sort of self-similar coarsening. Basically what's happening in this, as we'll see, is that the small crystals are melting and the big crystals are growing. And that's because we have a critical nucleation radius, which is actually increasing with time. And so the smaller crystals that are smaller than that critical nucleation radius are melting, and those that are larger than the critical nucleation radius are continuing to grow, and the whole distribution moves to larger length scales. So without, as I say, going into the detail of probability density functions, let me just illustrate the scales of this. Let's imagine that we have a distribution of crystal sizes, and I've left off all the overbars and things that designate means. So just understand that when I write A of t, I'm now not looking at a single crystal, but rather the mean of my distribution, A of t. And also this whole system will have a mean temperature, which I can define in a very precise way using enthalpy, T. But the important thing to realize is that this whole system is actually tending towards Tm, the equilibrium freezing temperature. Because I have all these curved interfaces, the temperature of any of these interfaces is below Tm. Okay, because of Gibbs-Thompson. Okay, because it's curved, the equilibrium freezing temperature is below Tm, and the mean temperature is below Tm. As the coarsening takes place, the mean temperature will approach Tm. Okay. So our Stefan condition, we've seen this several times before, rate of release of latent heat, thermal conductivity, the equilibrium temperature, which is now Tm minus 2 gamma over the mean radius. Sorry, in this, I apologize for that. That should be, oh, no. So I'm getting myself confused. That might need to be a little gamma. No, I think this is big gamma. That's big gamma. So this is the equilibrium temperature minus the mean temperature. Okay. So we are now looking at the individual particle scale, as it were. So each particle is growing into a sort of averaged environment at the mean temperature. So this is our far field temperature, which is evolving in time. Okay. And here I've just split out the different terms. We've got a term proportional to 1 over a, that's these two terms over a, and a term related to 1 over a squared. So we saw this before when we were looking at critical radius, nucleation radius. The difference here is that this t is a function of time. And I can keep these three terms in balance, all of them balancing, okay, but I have only two balancing relationships, for three variables, a, the temperature, and time. And so we're back to a situation where we're going to have a similarity solution, and the only time is sort of elapsed time. And if we just look at these two terms, we can see that a cubed looks like t, so a looks like t to the third, and the temperature difference, the undercooling below Tm is decreasing like t to the minus a third. Okay. So that's sort of the end of the story and where I'll stop so we can have a bit of a break before Sylvain. What have we learned this morning? Firstly, that diffusion-controlled solidification has this characteristic length scale of the square root of kappa t. Actually, it's square root of kappa t over s if the Stefan number is large, as it typically is. And that allows us the use of quasi-stationary approximation, which I'm going to make good use of in later lectures. We've seen that rapid solidification is limited by molecular kinetics. That's very important. And that solidification into a supercooled melt is morphologically unstable. And I'm going to pick up on that theme significantly in my next lecture on Wednesday. And finally, we've seen how surface energy both mitigates morphological instability and gives it some structure, and ultimately leads to coarsening of our microstructure. So I'll stop there. Thank you. I was going to say, there have been a few questions in the middle. I should have said it right at the beginning. I'm always happy for interruptions. And if you have any questions now, either in public or in private, I'm very happy to try and answer.
So here you either take into account the molecular either the curvature, you never mix that. Is it possible?
Yeah. Yes, and in fact, if I had done the morphological stability calculation rigorously, really I should have been in the S less than 1 regime, governed by kinetic undercooling, and then included that kinetic undercooling also in my stability analysis. And I've done all of that, and you can do it. It's just much messier on these slides. But yes, no, then the kinetic undercooling is G, the kinetic growth rate, times the difference between your equilibrium minus the actual temperature. The equilibrium would then be depressed by your curvature term, by the Gibbs-Thompson.
Most of the analysis you make is based on continuous medium approach, and then the rapid solidification limited by molecular kinetics is because it's not a continuum medium, in fact because you have molecules. Do you have an idea what the cutoff length is between those two? And is it
Um, interesting question. I I'm going to say a few molecular, but only a few probably. Continuum mechanics tends to be actually quite robust down to very small length scales. Something that Alan will talk about, pre-melted films, which really get down to the nanometer scale. People have measured things like fluid viscosity down to a few molecular diameters, and the fluid viscosity is already a continuum concept, but it works down to a few molecular diameters.